Today I want to discuss on the solar energy, on the solar radiation. Today's lecture I will cover what is the solar radiation, beam and diffuse radiation, parameters on which the solar radiation depends on the Earth's surface. Now, what is the solar radiation? Solar radiation, often called the insolation, is a general term for the electromagnetic radiation emitted by the sun. The solar radiation can be captured and converted directly or indirectly into the useful forms of energy such as heat and electricity using a variety of technologies. However, the technical feasibility and economical operation of these technologies at a specific location depends on the available solar resource. Solar radiation reaches the Earth's surface at a maximum flux density of about 1 kilowatt per meter square in a wavelength band between the 0.3 and 2.5 micrometer. The spectral distribution is determined by the approximate 6000 K surface temperature of the Sun. It is called the shortwave radiation and includes the visible spectrum. This solar irradiance at ground level varies from about 3 to 30 megajoule per meter square per day depending on the place, time and the weather. Its thermodynamic quality relates to the extreme white hot temperature of the source and so is much greater than from the conventional energy sources. Nuclear fusion reactions in the active core of the Sun produce the inner temperatures of about 10 to the power 7 K and an inner radiation flux of uneven spectral distribution. This internal radiation is absorbed in the outer passive layers, which are heated to about 5800 K and so become a source of radiation with a relatively continuous spectral distribution. The solar spectrum may be divided into three main regions. One is the ultraviolet region where the lambda is less than 0.4 micrometer. It covers the 5% of the irradiance. Second is the visible region 0.4 micrometer to 0.7 micrometer wavelength where it is covered 43% of the irradiance. And last is the near infrared region where the wavelength is greater than 0.7 micrometer. Approximately 52% of the irradiance will cover. The figure shows the spectral distribution of the solar irradiance at the Earth mean distance uninfluenced by any atmosphere. The area beneath this curve is the solar constant. G0 star is equal to 1366 plus minus 2 watt per meter square. This is the radiant flux density RFD incident on a plane directly facing the Sun and outside the Earth atmosphere at a distance of 1.496 into 10 to the power 8 kilometer from the Sun. At the Earth mean distance from the Sun actually. The solar irradiance or the solar radiation incident on the atmosphere from the direction of the Sun is the solar extraterrestrial beam radiation. Beneath the atmosphere at the Earth's surface, the radiation will be observable from the direction of the Sun's disk in the direct beam and also from the directions as the diffuse radiation. So what is the diffuse and the direct solar radiation? As sunlight passes through the atmosphere, some of it is absorbed, scattered and reflected by the air molecules, water vapor, clouds, dust, pollutants, forest fires, volcanoes, etc. So the radiation is divided in two types, that is the direct beam and the diffuse beam. So the radiation which are absorbed, scattered and reflected by the air molecules, water vapor, clouds, dust, pollutants, forest fires and volcanoes, these are called the diffuse solar radiation. The solar radiation that reaches the Earth's surface without being diffused is called the direct beam solar radiation. The sun of the diffused and direct solar radiation is called the global solar radiation. Atmospheric conditions can reduce the direct beam radiation by 10% on clear dry days and by 100% during the thick cloudy days. So we can say that note that even on a cloudless clear day there is always at least 10% diffuse irradiance from the molecular scattering, etc. The ratio between the beam irradiance and the total irradiance thus varies from about 0.9 on a clear day to 0 on a completely overcast day. The practical distinction between the two components is that only the beam component can be focused, so that the systems that rely on the concentrating solar power work well only in places with generally clear skies and a strong beam component. So now I want to discuss the parameters on which the solar radiation depends on the Earth's surface. Every location on the Earth receives the sunlight at least part of the year. The amount of solar radiation that reaches any one spot on the Earth's surface varies according to the geometry of the Earth and Sun, the rotation of the Earth, the latitude and the seasonal change, the atmospheric transmission, absorption and the reflection. So come to the first point, that is due to the geometry of the Earth and the Sun. The figure shows the Earth as the sphere. It rotates in the 24 hours about its own axis, which defines the points of the north and south poles N and S. Because the Earth is round, the Sun strikes the surface at different angles, ranging from 0 degree just above the horizon to the 90 degree. When the Sun's rays are vertical, the Earth's surface gets all the energy as possible. The more slanted the Sun's rays are, the longer they travel through the atmosphere, becoming more scattered and diffuse. Because the Earth is round, the frigid polar regions never get a high sun, and because of the tilted axis of rotation, these areas receive no sun at all during part of the year. The axis of the poles is normal to the Earth's equatorial plane. The figure shows that the sea is the center of the Earth. The point P on the Earth's surface is determined by its latitude phi and the longitude xi. The phi is positive for the points north of the equator, negative at the south of the equator. By international agreement, the xi is measured positive eastwards from the Greenwich, England. The vertical north-south plane through P is the local meridional plane. The E and G in the figure are the points on the equator having the same longitude as P and the Greenwich respectively. Noon solar time occurs once every 24 hours when the meridional plane CP includes the Sun as for all points having that. The heavy line on the earth is the equator. The adjectives autumnal, vernal, summer and winter may be used to distinguish the equinoxes and the solstices as appropriate for the season and hemisphere. Note that the summer and the winter solstices are respectively the longest and shortest days of the year, and in the some years occur on the 22nd day of the month rather than on the 21st. The 23.5 degree tilt in the Earth's axis of the rotation is a more significant factor in determining the amount of sunlight striking the earth at a particular location. Tilting results in longer days in the northern hemisphere from the spring equinox to the fall equinox, and longer days in the southern hemisphere during the other 6 months. Days and nights are both exactly 12 hours long on the equinoxes, which occur each year on around 23rd March and the 22nd September. So, if the line from the center of the earth to the sun cuts the earth's surface at P, then the declination delta equals to the phi, such that the declination is the latitude of the point where the sun is exactly over it at the solar noon. Therefore, the delta varies smoothly from plus delta 0, that is 23.45 degree at the midsummer in the northern hemisphere, to the minus delta 0, that means the minus 23.45 degree at northern midwinter. Analytically, we can say that the delta is equal to delta 0 sine 360 degree into 284 plus n by 365. The rotation of the earth is also responsible for hourly variations in sunlight. In the early morning and the late afternoon, the sun is low in the sky. Its rays travel further through the atmosphere than at noon, when the sun is at its highest point. On a clear day, the greatest amount of solar energy reaches a solar collector around the solar noon. So here the N is the day in the year where N is equal to 1 on January 1. So now the latitude and the seasonal change on which the solar radiation depends on the Earth's surface. The daily insolation, that means radiation, the capital H, is the total energy per unit area received on a surface in one day from the sun. So the capital H is equal to the integral of GT, the total radiation, dt, where GT is the total irradiance, and the figure shows the daily insolation in the northern and the southern hemisphere. So its seasonal variation arises from the three main factors: the variation in the length of the day, the orientation of receiving surface, and the variation in the atmospheric absorption and the weather. First, come to the point is variation in the length of the day. The number of hours between the sunrise and sunset is given by this expression, where the phi is the latitude and delta is the declination. The latitude phi is the 48 degree. For example, the capital N varies from the 16 hours in midsummer to the 8 hours in midwinter. Then in the polar regions where the phi is greater than 66.5 degree, then the tan phi tan delta may exceed to 1. So in this case, the capital N is equal to 24 hours in summer and N is equal to 0 in winter. The second point is the orientation of the receiving surface. The figure illustrates how the daily insolation varies with the latitude and the season. The seasonal variation at the high latitude is very great. The first figure shows that the horizontal plane at a location P is oriented much more towards the solar beam in summer than the winter. Therefore, even if the GB star remains the same in the beam radiation for horizontal plane equation, the factor cos theta z reduces to GBH in winter, and so it reduces to capital HH. The variation with the season and the latitude of the capital HH, the solar energy received on a horizontal plane on a clear day. In summer, the capital HH is about to 25 megajoule per meter square per day at the all latitudes. In winter, it is much less at the high latitudes, owing to the shorter day length, more oblique incidence, and the greater atmospheric attenuation. The cross sections through the Earth at the solar noon, showing the relation between the latitude pi, declination delta, and slope beta of a collector at P. Theta is the angle of the incidence on the north or south facing collector. The northern hemisphere in summer, the phi delta beta is greater than 0, and for the in figure B, the symmetrical example 12 hours later in the southern hemisphere, where the phi dot is equal to minus phi, delta dot is equal to delta, and the beta dot is equal to beta, and the theta dot is equal to the theta. The variation in estimated average daily insolation capital H on a surface at various slopes, beta as a function of time of year, for the latitude of 45 degree N with the temperature KT is equal to 0.50 and gamma is equal to 0 degree, and the ground reflectance is equal to 0.20. The variation in the atmospheric absorption and the weather. The clear sky radiation plotted in the figure is less than the extraterrestrial radiation, owing to the atmospheric attenuation and the scattering. This attenuation increases with the theta z, so the GB star is less in winter. Consequently, the seasonal variation of the clear sky insolation is more than due to the geometric effects and the atmospheric transmission, absorption, and reflection. How the radiation is transmitted through a cloudless atmosphere depends on the frequency of the radiation and the radiation absorptance of the gases and the vapors present in the atmosphere. Consequently, the gases, including the water vapor in the atmosphere, cause the Earth's surface temperature to increase on an average about the 30 degrees centigrade more than with no atmosphere. Moreover, the clear sky radiation is a somewhat notional quantity, since the weather conditions, especially cloud, vary widely and often the dominate received insolation. Now the last point, that is atmospheric transmission, absorption, and reflection. It is mainly effects occurring as the extraterrestrial solar radiation passes through the Earth atmosphere. The extraterrestrial solar beam radiation, the shortwave radiation, it is returned to the space as the shortwave reflected radiation. It is absorption in the atmosphere, causing the heating eventual re-emission as the long wave radiation. Third is the continuous in the forward direction within the angular cone of the sun's disk direct beam radiation. Fourth is the scattered or reflected out of the direct beam of the sun's disk yet incident on the Earth's surface diffuse radiation, subscript D. It is depends on the diffuse radiation may be subdivided as that the incident from the certain directions having an angular dependence, and also the remaining diffuse radiation having the little angular dependence. Now the atmosphere, transmission, absorption, reflection are shown in this figure. The temperatures of the Earth's upper atmosphere at about 230 K and the Earth's surfaces at about 260 to 300 K remain in the equilibrium at much less than the 6000 K temperature of the Sun. Therefore, the outward radiant energy fluxes emitted by the Earth's atmosphere and surfaces equal on average the incoming insolation. Both is almost 1 kilowatt per meter square. The outgoing far infrared wavelength band has wavelengths between about 5 to 25 micrometer called the long wave radiation, peaking at about 10 micrometer. Consequently, the short wave and the long wave radiation regions can be treated as the quite distinct from each other, which is a powerful analytical method in the environmental science. As the solar radiation passes through the gases and the vapors of the Earth's atmosphere, a complicated set of interactions occurs that reduces the flux density arriving at the Earth's surface. The interactions with the molecules, atoms and the particles include the atmospheric absorption almost 19%, causing the heating and the subsequent re-emission of the energy as long wave radiation. Scattering the wavelength dependent change in the direction so that the usually no extra absorption occurs and the radiation continues diffusely at the same wavelength. And last is the reflection on about 30% from the particulates, clouds and at the Earth's surface, which is independent of the wavelength. So even with the clear sky there is the reflection back to the space. Consequently, the continuing shortwave solar radiation in clear cloudless conditions at midday has the flux density reduced from 1.3 kilowatt per meter square in space to 1 kilowatt per meter square at the ground level. This maximum solar irradiance of the 1 kilowatt per meter square is an important parameter to remember. This is the shortwave solar radiation. Incoming solar is 100%. From them, the 4% is the reflected from the Earth's surface, 20% is reflected from the clouds, 6% backscattered by the air molecules. So the total 30% of the total reflected shortwave solar. In between the 100%, the almost 16% is absorbed by the H2O, ozone, carbon dioxide, methane and other GHG aerosol particles. 4% is absorbed by the cloud, so total 20% to the IR. So the 50% is almost average incident as the direct and diffuse shortwave radiation. For the long wave infrared radiation, the 20% net IR emission from the surfaces and 30% the other heat upwards from the surface. So total 50% going to the going from the surface. Out of this, the 20% passes through the atmosphere and the 80% of which are passes via the clouds. And from the absorbed SW, as the IR emission is the H2O, ozone, carbon dioxide, methane and other GHG aerosol particles and clouds, this is 20%. 6% from the passes through the atmosphere and 44% of the total passes via the clouds. So total the 70% outgoing long wave infrared. So net incoming short wave is equal to net outgoing IW, long wave infrared radiation. So now the radiation transmitted and absorbed by the atmosphere as a function of the wavelength. The figure 1 shows that the I in the curve at the top left, the distribution of the radiation from the source at the outer temperature of the sun. In curves at the top right, the distribution of the radiation from a range of temperatures 210K to 60K and 310K. So the slightly wider than the range from the top of the bottom of the Earth atmosphere. In solid field, the wavelengths of the solar downgoing radiation reaching the Earth's surface and of upgoing thermal infrared radiation passing out from the top of the atmosphere. The figure B shows that the percent absorption of the atmosphere across the full solar shortwave and the thermal long wave spectral regions. At left is the shortwave window. This only transmits the safe solar insolation such that it absorbs most of the short ultraviolet radiation, where the lambda is less than 0.3 micrometer, which would otherwise damage much biological life. Note that the molecular and the particulate scattering and absorption reduce the beam intensity at the ground level, even in a cloudless sky. We may note that having the average temperature at the surface of the Earth about 291 K, that is 14 degrees centigrade, allows the most surface water to be liquid and the photosynthetic reactions to progress. At right is the long wave window, which transmits the peak of the outgoing infrared radiation, but whose steep boundaries are mostly determined by absorption by water vapor and carbon dioxide. Note that a large proportion of upgoing thermal radiation from the Earth's surface is absorbed in the atmosphere. Absorption at these wavelengths also occurs in the solar radiative input, but the proportion in the total solar flux is smaller. The selective nature of the long wave absorption arises from the vibrational modes of the gaseous and vapor molecules with 3 or more than atoms like H2O, carbon dioxide, methane, N2O, etc. In effect, the concentration of these gases in the atmosphere affects the width of the window. The larger the concentration, the narrower the window, and the vice versa. A wider window leads to cooling of the Earth's surface. A narrower window leads to warming. However, the role of water is complicated because the increased Earth temperature leads to increased evaporation and vice versa. Increased evaporation leads to more cloud that reduces the insolation and therefore cools the Earth, and increased water vapor concentration, especially at high altitude, that narrows the long wave window, which leads to heating. Calculations by modeling indicate that the resultant role of water vapor on global temperature change is less pronounced than the carbon dioxide. The figure C shows that the separate absorption spectra of major gases and the water vapor in the atmosphere and the effect of Rayleigh scattering. In the long wave thermal region, water vapor and the carbon dioxide absorb significantly the infrared radiation upgoing from the Earth's surface and lower atmosphere. water vapor concentration varies greatly by region and season and may reach about 4% by the volume of the local atmosphere. But its globally averaged concentration does not change much. Thus, the fluctuations of absorption by water vapor may be of some significance in practical applications, but cloud is likely to be far more influential. This absorption of the long wave radiation increases the temperature of the atmosphere and hence the Earth's surface such that it causes the radiative forcing and the greenhouse effect. The Rayleigh scattering is the elastic scattering of light or other electromagnetic radiation by particles much smaller than the wavelength of the light. The particles may be individual atoms or molecules. Rayleigh scattering of the sunlight in the atmosphere causes the diffuse sky radiation, which is the reason for the blue color of the sky and the yellow tone of the sun itself. The shortwave ultraviolet radiation lambda less than 0.3 micrometer would damage the many life but is removed from the downgoing radiation mostly by the ozone in the upper atmosphere and by the Rayleigh scattering. However, even the small amount of the ultraviolet radiation transmitted is enough to cause the severe sunburn in the skin. The depletion of the atmospheric ozone therefore constitutes a major threat to the health of the humans and even more so to the plants. Hence, the concern about the depletion of the ozone in the upper atmosphere discovered in 1970s, which was shown to be caused by emissions of the chlorofluorocarbons and the related substances, which are man-made industrial chemicals. Although some of these substances are also greenhouse gases, so too is ozone. Ozone depletion is particularly strong in the high latitudes at the springtime, that is called the ozone hole. The Montreal Protocol 1989 is an international agreement to phase out the production and use of such substances and has proved effective in doing so. These transmission and the absorption characteristics of the atmosphere have the similarities with the glass, so the extra warming is called the greenhouse effect and the gases concerned are called the greenhouse gases, that is called GHG. The greenhouse effect is a natural characteristics of the earth and of the crucial importance of the global sustained ecology because the normal temperature increases allows most surface water to be liquid rather than the solid. However, the magnitude of the greenhouse effect depends critically upon the atmospheric concentration GHGs, in particular the H2 and the carbon dioxide. The geometry of the collector and the solar beam. For the collector surface, the slope beta, the angle between the plane surface in question and the horizontal in either hemisphere for a surface facing towards the equator, that is 0 less than beta less than 90 degree, for a surface facing away from the equator 90 degree less than beta less than 180 degree. The surface azimuth angle gamma, it is projected on the horizontal plane, the angle between the normal to the surface and the local longitude meridian. In either hemisphere for a surface facing due to the south, gamma is 0. Due to the north, the gamma is 180 degree. The west towards the gamma is 0 to the 180 degree and the east towards the gamma is equal to 0 to minus 180 degree. For any horizontal surface, the gamma is 0 degree. Now the angle of incidence theta. the angle between the solar beam and the surface normal. Now for the solar beam, the zenith angle theta z, this is the angle between the solar beam and the vertical plane. Note that the theta z and the theta are not usually in the same plane. The solar altitude, that is alpha s, which is called the 90 degree minus the theta z zenith angle, the complement to the zenith angle of the solar beam to the horizontal. Now the sun azimuth angle gamma s, it is projected on the horizontal plane, the angle between the solar beam and the longitude meridian. Sine convention as gamma, so on the horizontal plane the angle between the beam and the surface is gamma s minus gamma. The hour angle already I discussed. The omega, that is equal to the angle that is earth has rotated since the solar noon when the gamma s is 0 in the northern hemisphere. Now the angle between the beam and the collector. With the sine convention, the geometry gives equations essential for the solar modeling. The cos theta is equal to a minus b sine delta plus c sine omega plus d plus e cos omega and cos delta, where the a is equal to sine phi cos beta, b is cos phi sine beta cos gamma, c is the sine beta sine gamma, d is the cos phi cos beta, e is the sine phi sine beta cos gamma, and the cos theta is equal to the cos theta z cos beta plus sin theta z sin beta cos gamma s minus gamma. For several special geometrics, the complicated above formula simplifies considerably. For example, for a collector oriented towards the equator and the slope of beta is equal to the magnitude of the latitude phi, that means the gamma is equal to 0, then the beta is equal to phi in the northern hemisphere. When the gamma is equal to 180 degree, then beta is the minus phi in the southern hemisphere. Then the above equation reduces to cos theta is equal to cos omega cos delta. For a horizontal plane, the beta is equal to 0 and the first equation reduces to the cos theta z is equal to sin phi sin delta plus cos phi cos omega cos delta. Now these are the references from where I made the tutorials presentation. Thank you.